Now in this module I want to look at how you determine the effective height of jets. Now when water leaves a nozzle at a certain velocity, it will reach a certain height depending on a number of factors. This here is the formula that you need to determine the theoretical height of a jet of water. H equals v squared divided by 2g. That is the theoretical effective height. However, there are a number of factors that you affect this, and these are, first of all, it's going to encounter air resistance as it passes through the air, and this would be higher when the air pressure was higher, and it would reduce obviously if it was lower pressure. The water would also have to overcome the force of gravity, which would be acting upon the water, so to raise it, it's got to go against the force of gravity. And finally, you would experience some turbulence within the water stream itself. Now these factors are the reason that the effective height of a jet is lower than the theoretical. Now the effective height of a jet of water can be determined by this formula here. HE equals 2/3 times brackets h minus 0.113 times h squared divided by d, where HE is the effective height of the jet in metres, the h is the head, and d is the diameter of the nozzle. Let's do an example. Determine the effective height of a jet from a 25mm nozzle operating at 3.5 bar. Now firstly we need to determine the head pressure by converting the pressure into head using this formula, because it's got it in bar, you need to convert it into head pressure using this formula. H equals 10.19 times P, where H is the head in pressure and B is the pressure in bar. Okay, if you put in your own variables you get H equals 10.19 times 3.5. now that means that 3.5 bar pressure converts into 35.665 metres head. Now if you put this in our formula, as you can see, it comes out at 19.93 metres. This shows you that theoretically you should be able to create a jet 35.665 metres, when in reality it's more like 19.93 metres. So do you understand, it's quite a big difference. Let's do another example. Determine the effective height of a jet from an 18mm nozzle operating at 4 bar. Well, firstly we need to determine the head pressure by converting the pressure into head using the formula H equals 10.19 P. So you put in your own variables, and that means that 4 bar converts out at approximately 40.76 metres head. If you put this in our formula, this comes out at 20.22 metres, and it shows you that theoretically you should be able to create a jet 40.76 metres, when in reality it's more like 20.22 metres. As you can tell, it's a massive difference, and that's because of all the other forces that the water's got to overcome. Now, what would be the impact of changing the nozzle to 25mm and still maintaining the same pressure at the nozzle? Well, firstly we need to determine the head pressure. Let's put this out now by converting the pressure into head using this formula. Well, obviously this one here has not changed, so the pressure's the same at 40.76 metres. Now if we put the new nozzle size in our formula, as you can see here, this comes out at 22.16 metres, so there's still a massive loss. This shows you that very high effective jets are difficult to achieve, and increasing the nozzle size doesn't really have a major impact. It does change it, but it doesn't have a major impact. Now you do need to have high pressures to reach these heights, and if you can't use them, that's why I use turntable ladders and platforms, which enable you to discharge the water higher up. That's why you need these turntable ladders and platforms, because creating an effective jet from the ground is not very efficient, not very easy to achieve.